Hello everyone. Seamless steel pipes are commonly utilized for transportation of fluids like water, natural gas, waste, and air. It is frequently needed in various high-pressure, highly corrosive settings such as in the oil and gas, power generation, and pharmaceutical industries. To satisfy the requirements of the preceding applications, seamless steel pipes are produced using three different methods, which are the monocement plug mill process, the mandrel mill process, and the extrusion process. In this video, the monocement plug mill process is explained. By this method, seamless steel pipes are produced from a continuously cast billet weighing up to 7 tons. Seamless steel pipes with a wide range of diameters and wall thicknesses can be manufactured from these billets. The production procedure of the hot operation starts with the steel billets being placed in a rotary hearth furnace, where they are heated to a rolling temperature of 1250 to 1300 degrees Celsius over up to 9 hours. When exiting from the rotary hearth furnace, the surface of the billet is covered with scales which must be removed by high-pressure water. The steel billets, brought to rolling temperature, are placed into a round die and transformed into a hollow shell using a vertical 2,000-ton piercing press using a cylindrical mandrel up to 400 mm in diameter. This process, known as upsetting, involves elongating the hollow shell while maintaining nearly the same outer diameter. From the piercing press, the hollow shell goes to the cross-rolling mill. Initially, the remaining bottom from the piercing press is pierced with a force of about 3,200 kN. After that, the hollow is inserted into the rolling mill, where it is captured by the rolls in a spiral movement over the mandrel, forming a thick-walled hollow shell. The cross-rolling mill consists of two specially profiled work rolls driven in the same rotational direction. Their axes are inclined by about 3 degrees against the horizontal rolling axis. In the middle of the roll gap is an internal tool, a mandrel supported by a rod against an external abutment. The wall thickness of the hollow shell is reduced and equalized, and the outer diameter is adjusted as needed. Material elongation is about 150 to 200%, with a cross-sectional reduction of about 33 to 50%. After the rolling process is completed, the scale formed on the surface is blown off with pressurized water. After that, the thick-walled hollow shell is rolled into the final pipe using the pilger mill. The rolling tools in the pilger process comprise 2 ring dies and a cylindrical rolling mandrel whose diameter matches the inner diameter of the final pipe. The lubricated mandrel is located inside the hollow shell in a fixed position and rotated by the mandrel thrust block. The mandrel itself is tapered in the rolling direction. The dies have matching grooves on their circumferences. The machine provides the mill saddles with oscillating motion to generate the ring dies' oscillating rotary motion. During the forward and backward strokes, an external compression force is applied on the shell walls, resulting in a reduction of the hollow shell wall thickness in the same way as a rolling pin rolls out pastry. This process involves at least 2 passes over each material particle. A large number of small forming passes helps to ensure a constant wall thickness and nearly homogeneous material characteristics in the rolled pipe. This process results in stretching the hollow shell into the pipe, with elongation reaching up to 12 times the hollow shell length and a cross-sectional reduction of 80 to 90%. After rolling, the finished pipe is removed from the pilger mandrel. The mandrels must be replaced and cooled after each pipe due to the high temperature exposure. Additionally, for changes in the wall thickness of the final product necessitate the use of new mandrels of corresponding diameters. Immediately after the pilger mill, a saw cuts off the remaining hollow shell's end, known as the pilger head. It is often unevenly deformed front end of the pipe. After that, the pipe is reheated to a uniform temperature of approximately 900 to 940 degrees Celsius in a natural gas-fired walking beam furnace for further processing. In the stretch reducing mill, the final outer diameter is produced. This mill consists of 3 stands in a 2-roll arrangement, with the rolls forming a closed caliber and offset by 90 degrees in the rolling direction. After cooling, the finished pipes go to the straightening stage, where they are straightened on a roll straightening machine. Depending on the application, the pilger pipe undergoes additional processing steps or specific inspections. At the cutting stage, pipes are cut to the desired length according to customer specifications. On the cutting bench, the pipes are cut perpendicularly to the pipe axis, achieving a clean, burr-free cut surface. All pipes undergo thorough visual inspection here, with minor imperfections being ground out. Here, 2 surface treatment methods are available. Machining removes surface defects, especially for medium and high alloy materials. This is done to ensure a flawless surface and does not change the dimensional tolerances. Additionally, pipes are processed by external grinding according to requirements. This involves processing the pipes in an automatic machine with up to 7 grinding wheels of different grains and a finishing polish belt. When required, tubes can be shaped with ends upset according to standards, where the pipe's ends are heated to forging temperature with induction heaters and are then upset to the required contour. The forging is done by using either a mechanical or a mechanical hydraulic press. Moreover, pipes' ends can be threaded with different types of threads as required by the gas and oil industry. Threading is normally performed using CNC threading machines. In some cases, seamless pipes undergo a heat treatment cycle to increase their hardness and strength. This is done by heating the pipes to a temperature where their microstructure changes. This enables the pipe to be hardened by rapid cooling in the quenching process. The pipes are then tempered to the desired strength level in a tempering furnace. After finishing the pipes, they have to be inspected non-destructively using the electromagnetic test, and the pipe ends are then inspected using ultraviolet magnetic particles. During the electromagnetic inspection, the wall thickness is measured by phased array ultrasonic method. Moreover, ultrasonic testing is used to check pipes for longitudinal and transverse defects and ensure wall thickness compliance. Finally, before shipping to the customer, pipes are individually marked with material grade, order number, and other details to identify the pipe. The destination of each pipe is also marked. Then the pipes are strapped together in bundles and prepared for shipping. From here, the pipes are dispatched. Here, the production of seamless pipes is explained. Thanks for watching. If you enjoyed this video, please like, subscribe, and share it with others who might find it interesting. Drop a comment below if you have any questions or suggestions for future videos. Stay tuned for more industrial insights, and we'll see you in the next video.